Study of conformers. So by taking several examples, I am going to explain you how to analyze different conformers and how to write possible conformers for a particular compound. So in my previous classes, I explained you some simple molecules like normal ethane and also N-butane and 1,2-difluoroethane. Such kind of molecules I already explained you in my previous classes. Today, so I want to explain few more examples on this so that you will become familiar to write different conformers, possible conformers for a particular compound, and you will be also able to analyze which is more stable and which is less stable, which is more energetic and which is less energetic. Okay, so on the basis of some factors which can influence of their stability. Okay, so first of all I'll give you uh, the simple example, 1-chloropropane, right? CH2CL, 1-chloropropane. This can be write or written as like this: hydrogen, hydrogen, chlorine, okay, hydrogen, hydrogen, and CH3. Okay, so possible conformers for this molecule I can write here. As you already know, we can represent in Newman projection formula. The dot indicates the front carbon. Okay, this you assume this is the front carbon, and this is rear carbon or back carbon. Okay, on each carbon 3 substituents are there. Okay, so this dot indicates the front carbon. On this front carbon you have 3 substitutions separated with 120 degrees, right? And this circle indicates back carbon. It has CH3, hydrogen, and hydrogen. So that means the dihedral angle between the two planes is equal to 0. At 0 degrees, this molecule, this conformer exists as fully eclipsed conformer, right? Fully eclipsed conformer. This is fully eclipsed conformer. Okay, so on the 60 degrees rotation about CC single bond 60 degrees, so you will get the another possible conformer, chlorine, hydrogen, hydrogen, so hydrogen, CH3, and hydrogen. So if you rotate another 60 degrees, you will get this conformer, Cl, hydrogen, hydrogen, CH3, hydrogen, and hydrogen. So this is partially eclipsed conformer. So this is Gaussian, P Gaussian, or this can be called as Q conformer. Okay, and if you rotate another 60 degrees, you will get this conformer, chlorine, hydrogen, and hydrogen, CH3, hydrogen, and hydrogen. So this is staggered conformer or anti-conformer, and again 60 degrees you will get again partially eclipsed conformer, because this CH3 comes aligned with this hydrogen. Okay, so the next conformer would be partially eclipsed conformer. Okay, Cl, hydrogen, hydrogen, CH3, hydrogen and hydrogen. So this is partially eclipsed conformer. Again on 60 degrees rotation about CC single bond, you will get another conformer, chlorine, hydrogen and hydrogen, then CH3 and hydrogen and hydrogen. So this is M Gaussian conformer, M Gaussian or skew conformer, right? So finally, if you rotate another 60 degrees on CC single bond rotation, you will get eclipsed the beginning molecule or beginning conformer, right? So these are the possible conformers for 1-chloropropane or propyl chloride. Okay, so at 0 degree centigrade, the chlorine and CH3 are very near to each other, on top of each other. Okay, align with each other, and after 60 degrees rotation about CC single bond, you will get P Gaussian or skew conformer. Okay, and after another 60 degrees rotation, you will get this partially eclipsed conformer. Then again 60 degrees, you will get anti-conformer or staggered conformer. Again 60 degrees, you will get partially eclipsed conformer. And if you on 60 degrees rotation, again it will produce M Gaussian or skew conformer. So finally on 60 degrees rotation, you will get the fully eclipsed conformer. So these are the possible number of conformers for this particular molecule, chloropropane, right? Propyl chloride, right? So now, this is the first step. You need to write the possible number of conformers per a given particular compound. Okay, so in these conformers, we need to analyze which is more stable and which has more energy, and after that we have to write the energy diagram for that. Energy and energy on x-axis, dihedral angle on y-axis. By taking them, you can draw a graph for that. Okay, so that it is easy for us to analyze and determine which is more stable and which is more energetic, right? So in this, first let us try to understand about this fully eclipsed conformer. In fully eclipsed conformer, there is a eclipsed strain in this conformer. Eclipsed strain means the two bulky groups and all the substituents align on top of each other. They are in one line. They are very nearer to each other. Therefore, there is an eclipsed strain. And also there is a steric strain. Okay, there is a steric hindrance because two bulky groups or two hydrogens, they are each near to each other. Okay, chlorine and CH3, they are bulky groups, so they are very nearer to each other. Therefore, there is steric hindrance also, right? So because of that, they contribute instability or distability to the conformer. So whereas in P Gaussian or skew conformer, the chlorine and the CH3 groups are 60 degrees bond angle away from each other. Okay, so that the eclipsed strain will not be present in this P Gaussian conformer. So what about steric hindrance? There is no steric hindrance. Here I want to explain you one important thing after I analyze all of these things. Okay, so partially eclipsed conformer, you have eclipsed strain, steric strain. Okay, so they contribute distability to the conformer. So about anti-conformer, in this case the chlorine and the CH3 groups are opposite to each other. So the eclipsed strain absent and also steric hindrance absent. Okay, so there are no factors which can influence to distability to that molecule. But in this partial eclipsed also we have eclipsed strain and steric hindrance, right? And about this M Gaussian, these two are same. They are dynamic enantiomers. Okay, so because if you write these two conformers in the mirror image, you will find out that they are same. Okay, they are it is mirror image of this one, this is mirror image of that one, therefore they can be considered as dynamic enantiomers. Okay, you know already about what is enantiomer. Okay, non-superimposable mirror images, right? So this can rotate the plane polarizer light towards right, this can rotate left side. Okay, so both can be get cancelled, so that these two conformers are optically inactive conformers, right? So finally after 60 degrees, about 360 degrees, you will get the starting conformer which is fully eclipsed. Okay, so in these conformers, which one is more stable? Can you guess? I hope many of you say that anti-conformer is more stable, a staggered conformer is more stable. But I want to tell you that is not the right answer. The right answer, the most stable conformer in this molecule is P or M Gaussian conformers. Why? What is the reason? What might be the reason? You might think because there is a van der Waal attractions in between chlorine and CH3. Van der Waal attraction takes place between chlorine and CH3. In this M Gaussian also between chlorine and CH3. Van der Waal attractions takes place. So van der Waal attractions contributes to the conformer, the stability to that conformer. It brings down the energy and it contributes stability to the conformer. So why van der Waal attraction in between chlorine and CH3? So I already explained you about van der Waal interactions. Okay, so there is a chance of van der Waal attraction between two groups or atoms when the distance between those groups or atoms are more than that. Okay, the distance should be more than van der Waal distance between the two atoms or groups. Okay, two atoms or groups. Okay, if the distance between two groups or atoms is less than van der Waal distance in between them, then there is a van der Waal repulsion. Okay, when the distance is more than van der Waals distance, then there would be van der Waals attractions. Van der Waals attractions contributes stability to the molecule. Van der Waals repulsions contributes distability to the conformer. So here, in between this group and this group, there is van der Waals attraction. So that the final order of stability of these conformers can be written like this. So Gaussian conformer, it might be P or M Gaussian, is more stable than staggered conformer is more stable than partially eclipsed conformer is stable than fully eclipsed conformer. So this is the order of stability in this example. So this is the order of stability in this example. So Gaussian conformer is more stable than staggered and anti-conformer. Here actually, so there is no destabilizing factors in this conformer, even though in this there is a van der Waals attraction between these two groups, because the distance between the chlorine and CH3 is more than van der Waals distance. Okay, if the distance is more than van der Waals distance, there is a van der Waals attraction. If the distance is less than van der Waals distance, then there would be van der Waals repulsion. You need to understand that. Okay, so because of van der Waals attractions, Gaussian conformer is more stable than staggered conformer, even though there is no destabilizing factor in anti-conformer. Okay, so because van der Waals attraction contributes stability to the molecule, you need to remember that one. Okay, van der Waals attractions contribute stability to the molecule. Okay, so that is the important point you need to understand. So if you understand that, you can easily write the order of stability among these conformers. Okay, among these conformers, Gaussian conformer is more stable than staggered conformer because van der Waals attractions in Gaussian conformer. Okay, so I'll explain you the different example. So similarly, if you take 1-chlorobutane or butyl chloride, the same thing happen like the previous example. What I told you, what I explained you about propyl chloride. Okay, in butyl chloride, so there is a two groups exist on adjacent carbons. On the front carbon you have chlorine, on the rear carbon you have ethyl group. Okay, so the chlorine and ethyl group, when the conformer in Gaussian conformer, so there would be van der Waals attraction in between them. Therefore, it is more stable than staggered conformer or anti-conformer. The similar example you need to understand. Okay, propyl chloride or butyl chloride. In both the examples, you need to understand Gaussian conformer is more stable than staggered conformer, partially eclipsed conformer, and fully eclipsed conformer, because due to the van der Waal attractions in Gaussian conformer. Okay, so you need to understand that one. So next I'll give you some more examples like ethylene glycol. This is ethylene glycol. How we can write different conformers for ethylene glycol? Simple, right? So OH, hydrogen and hydrogen, OH, hydrogen and hydrogen. So this is dihedral angle is 0, that means fully eclipsed conformer. If CC single bond rotation 60 degrees, on rotation of 60 degrees, you will get Gaussian conformer. Hydrogen and hydrogen, hydrogen and hydrogen. So this is Gaussian conformer. P Gaussian as Q conformer, right? P Gaussian as Q conformer. Another 60-degree rotation, it will become partially eclipsed conformer. Hydrogen and hydrogen, OH, hydrogen and hydrogen. Okay, partially eclipsed conformer. Again 60 degrees rotation on CC single bond, you will get anti-conformer. OH, hydrogen and hydrogen, OH, hydrogen and hydrogen. This is anti or staggered conformer. Okay, again 60 degrees you will get partially eclipsed conformer. Again 60 degrees you will get M Gaussian conformer. Finally last 60 degrees rotation, that means 360 degrees rotation, you will get the beginning conformer, which is nothing but fully eclipsed conformer. Okay, so these are the possible conformers for ethylene glycol molecule. Ethylene glycol molecule. So first step, we did first step, that we write the possible number of conformers for a ethylene glycol. The next step, so what are the factors which can influence the stability of those conformers, and which is more stable and which is less energetic, and which is less stable and which is more energetic. Okay, those things you need to be analyzed. Okay, so in this case, so what would be the most stable conformer? Some of you think that anti or staggered conformer is more stable. You may think like that, but no, the Gaussian conformer is more stable, because there is a hydrogen bonding between this most electronegative atom and the hydrogen which is attached to more electronegative atom. Okay, there is a hydrogen bonding between this hydrogen and the more electronegative atom. Okay, so hydrogen bonding contributes to the conformer stability. It stabilizing factor, hydrogen bonding. As I said in previous example, van der Waal attraction. Van der Waal attraction is stabilizing factor. Also, hydrogen bonding also stabilizing factor. Whenever there is a possibility of hydrogen bonding, it stabilizes that molecule. That means it will become more stable than other one. Of course, in the staggered or anti-conformer, you don't have any eclipsed strain or steric hindrance, okay, or any destabilizing factors in that. But in this, stabilizing factor plays major role, thus hydrogen bonding. Therefore, the stability order in these conformers would be like this. Gaussian conformer is the most stable one, then the staggered conformer, and partially eclipsed conformer, finally fully eclipsed conformer. Okay, the stability order would be like this. Okay, in this case, in ethylene glycol, the reason why Gaussian or skew conformer is more stable than staggered or the remaining conformers, the reason is hydrogen bonding. Hydrogen bonding plays major role which contributes to that conformer the stability. Therefore, it is more stable than staggered or anti-conformer. So this is the way you need to analyze different given examples, and you need to determine which is more stable and which is more energetic and why. What are the reasons? You need to you should be able to explain. Okay, so in the previous example, van der Waals attractions contribute stability to the Gaussian conformer. In this case, hydrogen bonding, intramolecular hydrogen bonding. Okay, so here the hydrogen bonding, the distance between these two are very uh, very less. Hydrogen bonding, there is a possibility of weak hydrogen bonding, but more the what is eclipsed strain and steric strain, all these present in this fully eclipsed. Okay, but here the distance between the hydrogen and the more electronegative atom is very suitable for hydrogen bonding. Therefore, intramolecular hydrogen bonding plays major role in this example or in this conformer, so that there is no intramolecular hydrogen bonding possible in this conformer, anti or staggered conformer. Okay, so because of that reason, Gaussian conformer is more stable than staggered conformer. The second one is this one more stable, and the third one is partially eclipsed conformer, because the hydroxyl groups are at different places, but in fully eclipsed conformer, both the hydroxyl groups are in very nearer to each other. So because of that, the eclipsed strain is more in this than this partially eclipsed conformer. Okay, so this is the stability order for ethylene glycol conformers. Okay, so in this example, you need to understand the intramolecular hydrogen bonding. As I said in my first class, the factors which can influence the stability of different conformers, right? In that topic, I explained you about hydrogen bonding and van der Waals attractions or van der Waals repulsions, eclipsed strain, okay, and geminal repulsions and dipole repulsions. Okay, so all those and hyperconjugation, all those factors which can influence the stability of conformers. Okay, so you need to understand all these factors, then only you will be able to determine the right stability order or the energy order for a particular example, and you will be able to write the possible number of conformers also. Okay, so when you will be given an example, you need to first, you need to you will be able to write possible conformers for that particular example. Then you need to analyze what are the factors exist in this particular conformer. So you need to check about eclipsed strain, you need to check about van der Waals strain, it may be attractions or repulsions, you need to check about dipole repulsions, you need to check about hydrogen bonding, you need to check about hyperconjugation, and also you need to check about geminal repulsions. Okay, all these factors you need to check in that particular example. Then you will be able to understand which is more stable, and it is very easy for you to write the stability order for a particular conformer. Okay, I'll give you one more example on this. CH2 OMe and OH. For this example, which is more stable? First thing, what are the number of possible conformers for this molecule? Okay, the same thing. Okay, hydrogen and hydrogen, OH, hydrogen and hydrogen. On 60 degrees we will get OMe, hydrogen and hydrogen, OH, hydrogen and hydrogen. And another 60 degrees rotation about CC single bond, you will get partially eclipsed conformer, OMe, hydrogen and hydrogen, OH, hydrogen and hydrogen. So this is partially eclipsed conformer. So again 60 degrees rotation about CC single bond, you will get the anti-conformer, hydrogen and hydrogen, hydrogen, hydrogen and hydroxyl group. Okay, and two more 60 degrees if you rotate, you will get again partially eclipsed, again you will get Gaussian conformer. So finally you will get this fully eclipsed conformer. Okay, so for this particular example, so these are the possible number of conformers. Okay, so let us try to analyze which is